So in the first class today, we are going to talk about some fundamental concepts in physiological chemistry. Before every lecture, you will have a list of objectives. These objectives are listed in your syllabi. So whenever you have a question about what really you need to focus on to study for the exam, what you do is you refer to these objectives. You prepare your material in such a way that you need to come back to these objectives and you need to answer the question, can you identify the individual functional groups in a given structure? Can you classify the structures based on functional groups? And so on. If you prepare for your exams in such a way that you can answer each one of these objectives, you would do well not only on this particular class, but in every class. So, before learning various biomolecules, it is important to review and understand the environment in which these biomolecules exist. As you all know, water is essential for life. It covers about 2/3 of the Earth's surface. As a matter of fact, even the human body is comprised of over 70% water. Some of the fluids in the human body include blood, urine, and saliva. Even on a cellular level, the cytoplasm in biological cells is nothing but water. So the question is, what is it that accounts for the ubiquitous presence of water in living systems? The answer to that question is the structure of water. It is the structure of water which gives it unique properties that make it well suited for biological systems. Now, water is a polar molecule. It is a polar molecule because it has a positive side and a negative side called an electric dipole. Water molecules therefore have both a partial positive charge on the hydrogens and a partial negative charge on the oxygen. So what makes water polar? It is the structure of water. As you can see, water has one oxygen and two hydrogen atoms. Oxygen is an electron donor and hydrogen is an electron acceptor. Now, however, oxygen is very electrophilic, which means that even though it is sharing its electrons with hydrogen, it is keeping them very close to itself, giving it a partial negative charge. And therefore, hydrogen atoms in turn get a partial positive charge. This is what makes water a polar molecule. So to summarize, a polar molecule has a net dipole as a result of opposing charges, that is having partial positive and partial negative charges from polar bonds arranged asymmetrically. Okay, water is an example of a polar molecule since it has a slight positive charge on one side and a slight negative charge on the other. Now, to better understand polarity, let's take a look at carbon dioxide. In carbon dioxide, two oxygens share its electrons, each with a carbon, to form carbon dioxide. Now, even though the individual carbon-oxygen bond has dipole, the overall molecule has no dipole moment because the two dipoles are symmetrical and therefore cancelling each other. This is what makes carbon dioxide a non-polar molecule and water a polar molecule, because the bond in water is asymmetrical. Now, water molecules are bound together through intramolecular covalent bonds and intermolecular hydrogen bonds. Because of this polarity, the oxygen end of the molecule repels negative atoms like oxygen itself, while attracting positive atoms like hydrogen. Hydrogen, which is slightly positive, repels positive atoms like other hydrogen atoms and attracts negative atoms such as oxygen. This positive and negative attraction system helps water molecules stick together densely, which is what makes the boiling point of water very high, as it takes more energy to break these bonds between water molecules. Now let's take a look at different types of bonds. In order to further understand these bonds in water and why oxygen pulls the electron towards itself, we first need to understand the concept of electronegativity. Linus Pauling, the scientist who identified electronegativity, described it as the power of an atom in a molecule to attract electrons to itself. Basically, the electronegativity of an atom is its ability to attract electrons towards itself when it bonds to another atom. You just saw an example of oxygen in water molecule, where oxygen, being more electronegative, attracts the electrons more toward itself even though it is sharing them with hydrogen. The higher the electronegativity of an element, the more that atom will attempt to pull electrons towards itself and away from any atom it bonds to. Now let's take a look at some of the different types of bonding between atoms. The first one is the covalent bond. Two atoms form a covalent bond when they have a very small or nearly insignificant difference in electronegativity, which is described to be as less than 1.7 on the Pauling scale. Covalent bonding signals a complete sharing of electrons. Now, some of the examples of covalent bondings are between hydrogen atom and oxygen. Then you have another example, which is carbon that is bound to 4 hydrogens to form methane, is also covalently bound. Ionic bonding is the complete transfer of valence electrons between atoms. It is a type of chemical bond that generates two oppositely charged ions. In ionic bonds, one atom loses electrons to become a positively charged cation, whereas the other atoms accepts those electrons to become a negatively charged anion. In this example, the sodium atom in sodium chloride is donating its one valence electron to the chlorine atom. This creates a sodium cation, or a positively charged sodium ion, and a chloride anion, or a negatively charged chloride ion. Notice that the net charge of the resulting compound is 0. Ionic bonding happens when the difference in electronegativity of two atoms is greater than 1.7. And lastly, you have hydrogen bonds in the water molecule. A hydrogen bond is a very specific type of attraction between polar molecules that occurs when a hydrogen atom is bound to a highly electronegative atom such as nitrogen, oxygen, or fluorine. In that cases, when a hydrogen is bound to these atoms, it experiences attraction to the other highly electronegative atom. Now, just to summarize, this is the electronegativity of elements. You do not have to memorize these numbers, but what this table really tells you is that the electronegativity scale goes on increasing in the periodic table as you go from left to right, and it goes on decreasing in the periodic table as you go from top to bottom. So here you will see the highly electronegative atoms such as nitrogen, oxygen, fluorine are highly electronegative. Now, going back to the previous slide, let's take a look at the example between hydrogen and oxygen. Hydrogen has an electronegativity of 2.1, oxygen has an electronegativity of 3.5. The net difference is 1.4, which is less than 1.7. That's why they form a covalent bond. Likewise between carbon and hydrogen. Hydrogen has an electronegativity of 2.1, carbon is 2.5. It's very insignificant, a difference of 0.4. On the other hand, you have an ionic bond that happens when you have an electronegativity difference greater than 1.7 between sodium and chloride. Sodium, electronegativity of 0.9, chlorine, electronegativity of 3, so the net difference is 2.1. That's how this works. Now next, let's take a look at what are electrolytes. Electrolytes are substances that dissociate into cation and anion when dissolved in water and can conduct an electrical current, and therefore they are called electrolytes. Now, example is sodium chloride, potassium hydroxide. Okay, these electrolytes are essential to various bodily functions, and an electrolyte imbalance can be dangerous and even life-threatening depending on the clinical scenario. Or all our bodily fluids are electrolytes. That's one of the reasons that we get an electric shock. But more importantly, all the nerve, heart, and muscle cells need to have electric potential across the cell membrane, as that is how heart and muscles contract and nerve impulses get around. If an electrolyte imbalance is smaller that has been caused by, say, physical exertion, drinking a simple Gatorade is enough to restore it. In some severe cases of electrolyte loss, such as diarrhea or extensive vomiting, an intravenous route of administration may be necessary. A severe electrolyte imbalance can cause neurological and cardiac complications and may be fatal if not recognized and treated promptly. Now, there are two types of electrolytes. You have strong electrolytes and you have weak electrolytes. Strong electrolytes fall into three broad categories. You have salts, which is the NaCl here. You have strong acids, such as hydrochloric acid, and you have strong bases, such as potassium hydroxide. The weak electrolytes include weak acids and weak bases. Okay? An example here is the lactic acid. Okay? And lastly, you have non-electrolytes, which are substances that do not dissociate into ionic species, such as sugars and alcohol. Sugars and alcohol are therefore non-electrolytes. Now, electrolytes are substances which, when dissolved in water, break up into cations, which is the positively charged ions, sodium, potassium, hydrogen, and anions, the negatively charged ions. We say they ionize. Now, the difference between strong electrolytes and weak electrolytes is that strong electrolytes ionize completely, 100%, while weak electrolytes ionize only partially, usually on the order of 1 to 10%. That is, the principal species in solution for strong electrolytes are ions, whereas the principal species in solution for weak electrolytes is the unionized compound itself. Now, what do I mean by that? When you add potassium hydroxide to water, all of that is going to dissociate between potassium ions and hydroxide ions. Okay, there is going to be no potassium hydroxide left whatsoever. On the other hand, if you were to dissolve lactic acid in water, you notice the difference here between the single arrow and the double arrow here. What the double arrow really is telling you is there is always an equilibrium between the lactic acid and the ions that are formed after the dissociation of lactic acid. So only about 10% of lactic acid is going to dissociate into this lactate ion and the proton. And the equilibrium is going to keep on shifting back and forth. Okay? You can have this lactate ion combining with this proton going back to forming lactic acid. On the other hand, when you have strong acids or strong bases or salts dissociating, you can never have them going back to being the original compound. Potassium and hydroxide are never going to come back together to form potassium hydroxide. The proton here and the chloride ion are never going to go back together to form hydrochloric acid. That is one big difference between strong and weak electrolytes. So now let's take a look at acids and bases. Acid is primarily considered to be a proton donor. A base is considered to be a proton acceptor. Now, like I said, strong acids and strong bases dissociate completely, and their anions do not have a tendency to associate with the proton in solution, which means when sodium hydroxide has been ionized, the anion, the hydroxide ion, is not going to get together with the sodium ion to form sodium hydroxide. Likewise with HCl, the anion, the chloride ion, is not going to get back together with the proton to form hydrochloric acid. If you were to add stoichiometric equivalent amount of strong acid to a strong base, what you end up getting is salt and water. Okay. Now, strong acids have a tendency to dissociate more readily. Okay. An acid dissociation constant, or Ka, is a quantitative measure of the strength of an acid or a base in solution. Now, weak acids, on the other hand, dissociate less readily. That is why you have weak acids dissociating only to the order of 1 to 10% because they dissociate less readily, and therefore they have a very small dissociation constant, or a Ka. Now let's look at the pKa. Now what is a pKa? Okay, it's nothing but another way of saying of numbering the dissociation constant. Now these dissociation constants sometimes can be very cumbersome numbers. Now if you take a look at the dissociation constant of acetic acid, it's 1.74 times 10 to the power minus 5. Now that's not a number that anybody can easily remember. Okay, so that's where the pKa comes into picture. The pKa is nothing but the negative log of the dissociation constant. So the negative log of 1.74 times 10 to the power minus 5 comes out to about 4.75. It's a number that you can more easily work with, more easily remember. And that's what the pKa is all about. It's just another way of denoting the dissociation constant. The take-home point from this slide for you to memorize or associate with is that strong acids dissociate more readily, have a large dissociation constant. On the other hand, weak acids dissociate less readily. They have a small dissociation constant. Now in the example here, you have HCl, a strong acid with a dissociation constant of 10 to the power 3 or 1000. Compared to that, you have dissociation constant of a weak acid, acetic acid, which is 1.74 times 10 to the power minus 5, a really small value. Now equilibrium constant. Let's take a look at, before we talk about equilibrium constant, let's take a look at conjugate acid-base pairs. Now what do you mean by the word conjugate? Conjugate simply means in Latin that they are joined together. Okay, weak acid loses a proton to form a conjugate base. If you were to go back to the example of lactic acid a couple of slides ago, the negative ion or the anion that is formed on the dissociation of lactic acid, the lactate ion, is a conjugate base of lactic acid. Weak base gains a proton to form conjugate acid. Some of the examples of weak bases can be hydroxide ion. Hydroxide ion, if it gains a proton, forms a weak acid, which is water. Okay, now if you were to consider water to be a weak base, upon getting a proton, it's going to form the hydronium ion. Ammonium anion, NH2 minus, a weak base, on gaining a proton will form ammonia, which is the conjugate acid of the conjugate base. So I hope you appreciate how this is all relative. Okay, now the water molecule is a weak acid for the conjugate base, which is hydroxide ion. On the other hand, water in this example is a weak base for which the conjugate acid is the hydronium ion. Okay, if I were to give you a generic example, if HA is the conjugate acid, where H is the proton that makes it the acid, because acids, remember, are proton donors, upon dissociation, the conjugate acid HA is going to yield an anion, which is the conjugate base of this conjugate acid, and a proton. Now if the anion, the A minus or the conjugate base, were to gain a proton, it would turn into its conjugate acid. So HA is the conjugate acid for this conjugate base. So that's why they always go in pairs. That's why they are called conjugate acid-base pairs. So let's take a look at how do you calculate the equilibrium constant. Okay, in this example you have lactic acid, which is a weak acid, dissociating into the lactate anion and a proton. Or in a more generic case, you have HA dissociating into anion and proton. So the dissociation constant is calculated as the ratio of the concentrations of the right hand side, which is the dissociated ions, divided by the concentration of the unionized species. Okay, so lactic acid dissociates into lactate anion, which is the conjugate base of the conjugate acid, and a proton. Okay, so conjugate acid yields a conjugate base and a proton, so the dissociation constant is the product of the concentration of the protons times the concentration of the conjugate base divided by the concentration of conjugate acid. Now that we know what equilibrium constant is all about and how it's calculated, let's take a look at the Henderson-Hasselbalch equation, which is a step further from the equilibrium constant. So what really is Henderson-Hasselbalch equation all about? In chemistry, the Henderson-Hasselbalch equation is useful for estimating the pH of a buffer solution. It can also be used to calculate that if a particular molecule is placed in a solution of a particular pH, what fraction of the molecule will be ionized and what fraction will be unionized. Now, why do you need to care about this as a pharmacist? You need to care about this a lot because most of the oral drugs are either weak acids or weak bases. Therefore, they are part ionized and part unionized. The ionized portion is charged, which attracts the polar water molecules, therefore forming large complexes. These complexes cannot cross across the lipid cell membranes because they are bound to water and they are not lipid soluble. This is why the ionized part of the drugs cannot cross the cell membrane. Therefore, drugs are better absorbed in unionized form. So the Henderson-Hasselbalch equation, what really it does is it provides a relationship between the pH and the pKa, or the dissociation constant. The way the Henderson-Hasselbalch equation is calculated is really simple. You start off with the equation for the equilibrium constant, which is what you have here, and then you take a log on both the sides. So what you end up getting is this equation here. Okay, if you rearrange this equation, you have log of hydrogen ions, or rather the negative log of hydrogen ions, is equal to the negative log of Ka plus log of the concentration of anion to the concentration of unionized weak acid. So what really has been done here is this particular part has been moved on the left and this particular part is moved on the right. That's how they become negative. Okay, now log of H plus is equal to pH, right? And negative log of Ka is equal to pKa. So essentially, if you substitute these in this equation, what you get is pH is equal to pKa plus log of the concentration of anion to the concentration of unionized acid, weak acid. Now let's use this Henderson-Hasselbalch equation and solve a practice problem. So 0.20 moles of benzoic acid, a weak acid, and 0.1 mole of sodium benzoate. It's the anion, or the conjugate base of this conjugate acid, are dissolved in 1 liter pure water. What is the pH of this solution? So what you have been given is the dissociation constant of benzoic acid is 6.3 times 10 to the power minus 5. Okay. First thing you do is you calculate the pKa, which is fairly simple. All you do is calculate the negative log of the dissociation constant, and I would really suggest you to plug these numbers into your calculator and figure out how to calculate the negative log. So the negative log of the dissociation constant of benzoic acid comes to about 4.2. At this point, I want you to pause this video and I want you to go back to the Henderson-Hasselbalch equation, plug in these numbers using what you have been given in the practice problem and try to solve it for yourself. Okay, I want you to find out what the pH of the solution is using the pKa, the concentration of the anion, sodium benzoate, which is 0.1 mole, and the concentration of the weak acid, which is 0.2 mole. So, if you were to substitute these values in that equation, what you get is pH is equal to pKa 4.202 plus log of the concentration of the anion, which is zero point 0.1 moles of sodium benzoate, to the concentration of the weak acid, which is 0.2. So essentially it comes down to log of 0.1 to 0.2, which is nothing but log of 0.5. If you calculate the log of 0.5, it comes to minus 0.3. So the pH of this particular solution is 3.9. And this is one of the practical applications of Henderson-Hasselbalch equation. Now let's move to one of the more important concepts, ionizations of weak acids and weak bases. So when the pH is equal to the pKa, there are equal amounts of protonated and deprotonated forms. Okay, this is what you have to remember. When the pH is equal to pKa, you will have equal amounts of the protonated form and equal amounts of deprotonated form. Now this goes for a weak acid. For a weak base, you will have equal amounts of deprotonated form and equal amounts of protonated form, BH+. Now one more thing I want you to remember is the weak acid here is protonated but unionized. Okay, do not confuse protonation with ionization. A weak acid is protonated and therefore unionized. When it loses its proton, it becomes ionized. It gives you the negative anion. On the other hand, a weak base, when deprotonated, is unionized. Because remember, weak acid is a proton donor, weak base is a proton acceptor. So a weak base here is deprotonated and unionized. However, when it gains a proton, it becomes protonated and ionized. Okay, so now when the pH is less than pKa, the protonated form predominates, which is a fairly easy thing to visualize. Now, when you say the pH is less than pKa, this is the pH scale going all the way from 1 to 13. Now, if you were to be at a really low pH, okay, where let's say you are at a pH of 2, okay, it's an extremely acidic pH. In other words, there is an abundance of protons. So what is really going to happen is, because there is an abundance of protons, these protons are trying to go and latch onto whatever they can, and they are going to protonate the compound. So therefore, when the pH of a particular medium is less than the pKa of the particular drug, it is always the protonated form that is going to predominate. Okay, on the other hand, when the pH is greater than pKa, it's always the deprotonated form that is going to predominate. So in other words, you have a weak acid in acidic environment is going to be always protonated. It's always going to exist, more of that is going to exist in the HA or in unionized form. On the other hand, if you have a weak base in a medium where the pH is less than the pKa of that weak base, it's always going to be protonated, predominantly in the protonated form. And likewise, it's exactly opposite on the right hand side, or when the pH is greater than pKa. When the pH is greater than pKa, the deprotonated forms predominate. Now again, do not get confused between protonated and ionized. Okay. So to summarize, acidic drugs are better absorbed at a lower pH. The reason being, you have more of them in unionized form. Okay, drugs are always better absorbed when they are unionized, and therefore basic drugs are better absorbed at a higher pH. Okay, because basic drugs are deprotonated or unionized in basic pH. Now let's use these concepts that we've worked on so far and solve a practical problem. A practical problem that will tell us how much of the drug is ionized and how much is unionized. So there is a formula that tells you what percent of the drug will be ionized. That particular formula is given by 100 divided by 1 plus 10 to the power x, where x is -1 for acidic drug or +1 for basic drug, times pH of the medium minus pKa of the weak acid or weak base that's in the problem. So the problem statement states that aspirin is a weak organic acid with pKa of 3.5. What percent of dose will be in lipid soluble form at stomach pH of 2.5? So basically you have been given all the information. Like in the previous problem, I want you to take a minute, pause the video, plug in these numbers and try to come to the answer. So remember again, x is -1 for acidic drug. So you have to plug in the -1 here and solve this equation. So let's see what you've got. So the solution is 100 divided by 1 plus 10 to the power of x is -1, times pH of stomach is 2.5 minus the pKa of aspirin is 3.5. So it comes to 100 divided by 1 plus 10 to the power -1 times -1. So that's +1. So 100 divided by 11 is equal to 9.1%. So is 9.1% your answer? No. What 9.1% is the percent drug ionized. What you've been asked is what percent of the dose will be in lipid soluble form at stomach pH of 2.5. So what it's really asking you is what percent of dose will be in unionized form, because remember, when the drug is ionized, it forms these large complexes with water molecules that makes it impossible for the drug to go across the cell membrane. So in order for a drug to go across a cell membrane, it has to be in lipid soluble form, or in other words, it has to be unionized. So if 9.1% of your drug, and that's what this particular formula solves for, it solves for the percent drug ionized. If 9.1% is ionized, around 90.9% of the drug is unionized. So approximately around 90% of the drug will be in unionized form and therefore will be lipid soluble and therefore will be available to the patient. Buffers. Now what really is a buffer? A buffer is a solution that can resist pH change upon the addition of an acidic or basic component. A buffer is able to neutralize small amounts of added acid or base, thereby maintaining the pH of the solution relatively stable. This is very important for physiological processes and reactions which require specific and stable pH ranges. Buffer solutions have a working pH range and capacity, which dictates how much of acid or base can be neutralized before the pH changes and the amount by which it will change. Now typically the buffering capacity is 1 unit above and below the pKa. To effectively maintain a pH range, a buffer must consist of a weak conjugate acid-base pair, meaning either a weak acid and its conjugate base or a weak base and its conjugate acid. The use of one or the other will simply depend upon the desired pH when preparing the buffer. Okay, and now in this example here, you have lactic acid which has a pKa of 3.86. Okay, so what you have on the x-axis here is the pH. So that's going to tell you how much of the pH is being changed when you have lactic acid as a buffer. And on the y-axis you have the equivalence of base, or in other words, simple words, base is being added to that particular medium containing lactic acid. So you will see that the pH is not really changing as much even if you add a lot of base, around 1 unit plus and minus the pKa of lactic acid. So if you go around 2.8, which would be I think around right here, to around 4.8, which would be around right here, you'll see that the pH is relatively stable. However, beyond that range, the pH fluctuates very rapidly, even with the minute addition of some base. So below 2.8, even minute addition of the base is changing the pH. You'll see how this particular steep change is indicating a steep change in pH. Likewise, around more than 4.8. The same goes for another buffer, which is the ammonium, which is weak, uh, a weak base. It has a pK of 9.25. So typically it's going to be a good buffer between the pH of 8.25 to 10.25. So we'll see that the pH relatively stays constant as indicated by the straight line between that range. However, if you drop below that range, there is a drastic change in the pH. Now, why are buffers physiologically important? Buffers are important because impairment of the blood buffering system can result either in acidosis or alkalosis. Now, what really is acidosis? It can happen in multiple ways. You have respiratory acidosis that happens when carbon dioxide levels in your body increase. Respiratory acidosis is also known as respiratory failure. It's a condition that occurs when the lungs can't remove enough of the carbon dioxide produced by the body. This excess carbon dioxide causes the pH of blood and other bodily fluids to decrease, making them too acidic. So acidosis occurs when the pH of blood falls below 7.35, which is the normal pH of the normal pH range of blood is between 7.35 to 7.45. Another form of acidosis can be metabolic acidosis, which occurs with lactic acid formation. Now, if any of you have probably run a half marathon or a marathon or had a strenuous workout, you will see that the following day you feel very sore. That is nothing but metabolic acidosis, a buildup of acid in the muscles. Alkalosis, on the other hand, is excessive blood alkalinity caused by loss of acid from the blood, okay, which is called metabolic alkalosis, or by a low level of carbon dioxide in the blood that results from rapid or deep breathing, again called respiratory alkalosis.